So we're going to review operational amplifiers. Let's first start off with reviewing concepts from circuits 1. So what did we learn in circuits 1? Before that, let's review Ohm's law. The voltage across a resistor is V1 minus V2, the difference of the voltage difference across the resistor, and that is equal to the current that goes through the resistor times the resistance of the resistor. That's a quick review of Ohm's law. And what's the three steps of analyzing an op-amp circuit? So first, we're going to know that this is the non-inverting input and this is the inverting input. The current that goes through these inputs is 0 amps. So there is no current that goes through these. The second thing we're going to do is we're going to highlight the node across these inputs. So the node over here, and these inputs are actually virtually shorted, so it's going to have the same potential as the node over here. Now we're going to draw a KCL at this node, and this is the current from our voltage source, and this is the current that's going through the feedback resistor. We call it RF. Let's call this I1, I2. Now using KCL, Kirchhoff's current law, current in is equal to current out. So I1, that's the current that goes inside the node, is equal to I2 plus I guess, which is 0, so it doesn't really matter. So we know from the KCL that the current that goes through this resistor is equal to the current that goes through that resistor. And let's use the Ohm's law to figure out what's our output voltage. So let's expand on these terms and go back to Ohm's law. So the current is going to be V1 minus V2 divided by R. And over here, I1 is going to be 3 volts. This one is just 3 volts over here. So it's going to be 3 volts minus, so our non-inverting input is actually grounded. So the inputs of the op-amps is actually ground. So this one is going to be 0 volts. So 3 minus 0 divided by the resistance. So 5 kilo ohms. We can write it as 5,000 ohms is equal to so over here it's 0 volts, and over here it's V out, so it's going to be 0 minus V out divided by 15,000 ohms. Now we rearrange to get V out is equal to negative V out is it doesn't matter. V out is equal to 15,000 divided by 5,000 into 3, which is 9 volts. So that's the basic review of what we learned in Circuits 1 about an op amp. And here's another example of an op amp where we just follow the same 3 steps. The current that goes over here is 0, the current that goes over here is 0, and we highlight the node. Since one of our inputs is grounded for the op amp, this node over here is also ground. So we know the potential here is 0 volts. And then over here, let's not use these values for now. Let's write a symbolic expression. So let's label our currents. That's the third. This is part of the second step. It's I1. This is I2. And this is I3. And this is IF. If we do a KCL here, let's write down all our current in, which is V1 over R1 plus V2 over R2 plus V3 over R3, and that is equal to all the current that leaves this node. So this is 0, so we're not going to write that down. We're going to write IF, and IF is 0 minus V out, so it's going to be minus V out divided by RF. And when we rearrange this equation, V out is negative RF times whatever is over here. Oops. Let's write that down here. So these are our examples from Circuits 1. That's a quick review of what we learned. So what's the purpose of an op amp? Op amps take whatever input voltages you have. It can like amplify it to be a higher voltage or a lower voltage. It can essentially do a lot of things. It can even calculate, do mathematical operations for us, right? Which we're gonna go through. But like a common example for an op amp is actually in a phone, where you amplify a voltage. Your phone battery. Let's say this is a phone, right? It has a battery. Inside the phone there is like a battery, right? And there's gonna be a really tiny resistor here. It's like super, like, I don't know, it's like not enough voltage at all. Essentially, it's kind of like a wire, but an op amp is used here to amplify whatever tiny voltage difference this has, right? And when it's amplified here in an op amp, right, this voltage signal is read by a sensor, and because it's so amplified, it knows what essentially is going to be like how much voltage across our battery is going to be, and that's how our phone can tell how much charge we have left, right? This is what an op amp chip looks like. This is what you're going to use in your circuits lab, right? That's what the chip looks like. This is what we discussed. It can invert, can add, differentiate, a buffer. It's pretty useful. Yep. So an op amp has like a lot of transistors, capacitors. It's a complicated circuit, but it's always easy to simplify it with a triangle, right? And nobody cares about what's inside the op amp. People just care about what the op amp does, right? That's what the point of an op amp is. Here's a pinout diagram. That's going to be very useful for your circuit labs, right? And another thing is an op amp is an active device. You're going to learn that more in electronics, but what that essentially means is that it needs to be powered by something, right? It's not going to amplify or do anything with the output voltage if you don't power the op amp. And that's going to come out in the next part, which is gain, right? That's usually the the ratio of output with input. But another thing we didn't cover in circuits 1 is that there is a linear limit to an op amp. So here's a graph between the output and the input, and there's going to be a linear range depending on whatever inputs you put here, right? Let's say in our equation over here, our calculations tell us that it's 9 volts, but if our power supply is only giving it 6 volts, negative 6 volts, right? This is never going to be 9 volts. It's always going to be 6 volts, regardless of how big, your input supply is, or how small your input resistor is. It's always going to be 6 volts. It's going to be stuck at 6 volts, and the graph is simply just going to look like this. It's just going to be like, you have a negative 6 volts here, and if your input is going to be negative something, negative infinity, it's just going to be stuck at whatever linear limit it has, right? Yeah, it's called saturation. And here is a model of an op amp. This is what we use as an equivalent model using a dependent source. So that's another easy way to know what an op amp looks like. So if we go here, to explain how this model works and is equivalent, and how we even came to the other model. So in an ideal op amp, which we were looking at earlier in circuits 1, the internal resistance is infinity, right? And we know by Ohm's law, the voltage difference, which is Vp over Vn, is going to be IR. And if we have infinite resistance, our current is going to be 0. And if our current is 0, there is going to be essentially no voltage difference across this resistor, right? And if there is no voltage difference across this resistor, it's essentially just working as a wire. That's why we have a short, a virtual ground, you could kind of call it. That's why our non-inverting inputs and inverting inputs have the same potential. And because our voltage difference is 0, this is the output gain, you could say, is also going to be 0 volts. or it's actually going to be undefined. Like you wouldn't actually know what it is. And so whenever we have, let's say, a voltage source here, which is like 5 volts, and then we have a feedback resistor. That's one way of controlling our output voltage. You can change whatever value you have of the feedback resistor or change your input signal, and then you get a controlled output voltage. But in a real op amp, there's always some resistance here. And this is not 0, this is like a super small value. And this isn't infinity, it's actually some really big value over here. And like it's gonna have a pretty big effect. It's gonna have a lot of gain. But it's not, since it's like a super big value times a super small value, it's gonna be a super small value. And we can see that in the next slide, where they do 2 separate calculations, one using an ideal op amp and one taking in factor of these resistances, right? And when you take in factor of these resistances and this dependent source values, you get a gain of 4.9999975, which is like, well, what we did earlier with another example. If you follow those steps, you just get 5, right? So with the non-ideal case, it's still very similar. Like we get the gain that we want. So let's look at the different examples of the operational circuits that we were talking about earlier. The summation, the addition, subtraction, and so these are very useful circuits. Essentially, these circuits are completing an operation, right? This circuit is doing an integration of our input value, and is the constant that is multiplied by, and it does an integration of our input signal. So that's a really useful way to know how much essentially you can kind of figure out how much power you consumed with a circuit like this. And that's what the phone example was using earlier. And over here you get an ideal differentiator, which is minus RC, that's the constant, and you get a differential of this input signal. So these circuits are very useful if you want to do mathematical operations on signals, which computers are going to have a really hard time doing, and because these essentially have like no delay once it's in steady state. Right, and we're gonna finish off with like a difficult example. First step, we're gonna label our currents. There is no current going through these inputs. Second step, we're gonna label the nodes here. So this node has some potential, and that node is also equal to this node because they're shorted virtually. Right, and then we're gonna label the currents. So over here there is a current I1, there is a current I2, Now we know that I1 is equal to I2 because the current that goes in is I1, the currents that go out is I2, and it's this one, and that is 0, so it's just I2. So I1 is equal to I2. Now we know the potential across this node is V1, but we don't know what's the potential across this node because it's not ground like these examples, so it's not 0. It is some value though. How do we find that value? So let's look at this circuit. We know this input is V2, right? And essentially this is a voltage divider, like the equivalent of the circuit is just going to be plus minus V2. Oops. And this thing is ground, and over here is also grounded. R3, R4, and we just want to find the potential over here, which is gonna the potential across here, across this node here between R3 and R4 is simple voltage divider, which is V2. Or we can call this a op amp. Op amp. Amp. Let's just call it that. V amp. It's just gonna be V2 times R4 divided by R4 plus R3. So now we know the potential here is equal to V amp. Let's erase this. Oh yeah, V amp is going to be so in our case, it's simpler to just use a calculator value. So you get 1.25 volts, and essentially I1 is going to be 4 minus 1.25, because that's our potential that we calculated at the op amp inputs, divided by 10,000 ohms, and this is I2 is going to be 1.25 minus V out divided by 50,000 ohms. If we rearrange V out, we get negative 12.5 volts. So that's all for today. That's a quick understanding of how op amps work. See you